Welcome to my dear students. My name is Professor Kiran Mojad, Physics Department, S.V.K.T College in Devlalikan. Today we have discussed the characteristics of simple harmonic motions. Last lecture we have discussed the simple harmonic oscillators, their mathematical expressions, linear simple harmonic motion and their differential form of linear simple harmonic motions and their equations of linear simple harmonic motions. Learning objectives. First, concept phase of simple harmonic oscillators. Discussion of periodic time and frequency of simple harmonic motions. Concepts of velocity and acceleration in particular particle in S.H.Ms. What is the total energy in simple harmonic motions? Today's session agenda. The phase of simple harmonic motions, periodic time and frequency of simple harmonic motions, velocity and acceleration in particular particle in simple harmonic motions, the total energy in simple harmonic motion. This topic we have discussed in these sessions. First, phase of simple harmonic motion. The displacement at an instant is given by the x is equal to a sin omega t plus phi. Last lecture we have derived these equations. The angle omega t plus phi is called a phase of angle or simply phase of simple harmonic motions. The phase of motion at t is equal to 0 and phi t is 0 is phi and is called as the particle phase constant or epoch or starting phase of the motion. The phase of the oscillators the continuously change with time, but epoch phi it depends upon the initial conditions at which the oscillator is set into oscillations. The displacement versus time graph for phi is equal to 0 and phi is equal to pi by 2 is shown in these figures. For phi is equal to 0, the displacement means start to 0 and phi is equal to pi by 2 start to plus minus a. This is the a is the amplitudes. Period time of simple harmonic motion. The period of simple harmonic motion is defined as the time taken by the particle to complete one oscillations. After every time t, the particle will have the same position, velocity and the same direction. The displacement of a particle at any instant is given by x is equal to a sin bracket omega t plus phi. If the time t is increased to t plus 2 pi omega means the add to t plus 2 pi omega. The displacement at this time is x dash is equal to, this is a new displacement, x dash is equal to a sin curly bracket omega bracket t plus 2 pi upon omega bracket close plus phi curly bracket close. The x dash is equal to a sin omega t plus 2 pi plus phi is equal to a sin omega t plus phi plus 2 pi or phi, the rearrange in these steps. Therefore, is equal to a sin omega t plus phi cos phi plus cos omega t plus phi sin phi. Here use the sin a plus b formula. Therefore, sin a plus b is equal to sin a cos b plus cos a sin b. Here a is omega t plus phi and b is 2 pi. Therefore, is equal to a sin omega t plus phi, and x dash is equal to x. Here a sin omega t plus phi and cos phi, the cos 2 pi is 1 and sin pi is 0. Therefore, cos omega t plus phi is 0. Therefore, remaining term means a is equal to sin omega t plus phi, and therefore x dash is equal to x. Thus, after time 2 pi upon omega, the displacement is repeated itself. This time is called periodic time and denoted by capital T. Therefore, capital T is equal to 2 pi upon omega, and omega is equal to under root k upon m. Therefore, T is equal to 2 pi under root m upon k. Thus, the period depends on mass m and force constant k, but it is depend on the amplitude of oscillations. We have T is directly proportional to under root m for constant k, and T is inversely proportional to under root k for constant m. If we encounter an oscillating body with a period that does depends on the amplitude, the oscillation is not simple harmonic motion. Next, frequency of simple harmonic motion. The number of oscillations completed by a particle per unit time is called frequency of the oscillations. It is reciprocal of the periodic time t. Thus, we have nu is equal to 1 upon t is equal to nu is equal to 2 pi under root k upon m. Nu is equal to omega upon 2 pi. And therefore, omega is equal to 2 pi mu. The frequency of simple harmonic motion depends upon the force constant and mass but independent of amplitude of oscillations. The frequency of simple harmonic motions depends upon the force constant and mass but is independent of amplitude of oscillations. The omega is called the angular frequency of oscillations. Its unit is radian per second. For given value of m and k, the time of one oscillations or frequency is the same whether the amplitude is large or small. Next, the velocity of particle in S.H.M means simple harmonic motion. The velocity in simple harmonic motion varies with time. The displacement of particle performing simple harmonic motions at an instant is given by x is equal to a sin omega t plus phi. The velocity of the oscillation is the rate of change of displacement. Therefore, the velocity at an instant is v is equal to dx upon dt. Therefore, v is equal to, substitute the value of x is equal to a sin omega t plus phi in above equation. D is equal to square bracket a sin omega t plus phi bracket close square bracket close upon dt. Here a is a constant, this is the out of derivative, therefore a. The derivative of sin omega t plus phi is cos omega t plus phi. Then derivative of omega t, the omega is a constant, this is the out of derivative. Then dt upon dt is 1 plus derivative of phi is a constant, derivative of constant is 0. Therefore, v is equal to a omega cos omega t plus phi. Thus, when compare the equation of displacement and velocity at any instant we can write the equation once as v is equal to a omega under root 1 minus sin square omega t plus phi. V is equal to omega under root a square minus a square sin square omega t plus phi. V is equal to omega under root a square minus x square. There, here a sin omega t plus phi is x. So substitute the x in this term. This equation gives the magnitude of velocity of a particle performing simple harmonic motion in the term of its displacement and amplitudes. Hence, at mean position, the velocity is a maximum, and at the extreme position, the velocity is 0. The negative sign shows the direction of velocity in oscillatory motion. Change in sign shows the change in direction of motion. The position x is equal to 0, the velocity v is equal to plus minus a omega. And the position x is equal to plus minus a, the velocity is equal to 0. And position x is equal to plus minus a by 2, means half amplitudes, v is equal to plus minus root 3 by 2 into a omega. At x is equal to plus minus a, v is equal to 0. This is called instantaneous stops. When the particle moves from equilibrium position to extreme position on either sides, its velocity goes on decreasing. At extreme position, it becomes 0 and suddenly particle turns back. The velocity is maximum at t is equal to x is equal to 0. Its magnitude is v max is equal to a omega. The acceleration is a rate of change of velocity. Therefore, the acceleration is alpha is equal to d v upon dt is equal to d square x upon dt square. Therefore, x is equal to a sin bracket omega t plus phi. Therefore, alpha is equal to a minus a omega square sin omega t plus phi. There substitute a sin omega t plus phi is equal to x. Therefore, alpha is equal to minus omega square x. The negative sign shows that the acceleration is in direction opposite to the displacement. That is, it is directed toward the mean position. Thus, the acceleration and displacement are 180 degree out of phase. At x is equal to 0, the acceleration will be 0. At x is equal to a, the acceleration is minus a omega square. This is a minimum acceleration. At x is equal to minus a, the alpha is equal to a omega square. Since omega square is a constant, therefore, alpha is directly proportional to minus x. The acceleration in linear simple harmonic motion is proportional to the displacement from mean position, and its direction is opposite to the displacement. Next, energy in simple harmonic motion. The total mechanical energy of a particle of mass m performing simple harmonic motion at any instant is sum of kinetic energy and potential energy at that instant. First, the kinetic energy. The kinetic energy K of the particle performing simple harmonic motion is given by K is equal to half mv square, where m is the mass of the particle and v is the velocity at an instant. We have v is equal to omega under root a square minus x square. Therefore, k is equal to half m omega square into a square minus x square. Next, the second, the potential energy. The potential energy of the oscillators at position x from mean position is given by v is equal to half kx square. Since k is equal to m omega square, we have substitute k is equal to, in above equation, v is equal to half m omega square x square. The total energy. The total energy of the particle performing simple harmonic motion is sum of kinetic energy and potential energy. Therefore, E is equal to kinetic energy plus potential energy. Therefore, substitute the potential and kinetic energy equations in above equation. E is equal to half m omega square bracket a square minus x square bracket close plus half m omega square x square. Solve these equations. First, solve this bracket half m omega square a square minus half m omega square x square plus half m omega square x square. The last two terms are same but sign are opposite. Therefore, last term are cancelled. Therefore, E is equal to 1 upon 2 m omega square a square. Since k is equal to m omega square, substitute this in above equation. Therefore, E is means total energy is equal to half k a square. Since for a given simple harmonic motion, m, omega and a are a constant, the total energy is constant at a instant of simple harmonic motion. First, at extreme positions, suppose the particle is in extreme position, x is equal to plus minus a. Therefore, potential energy is equal to E means total energy and kinetic energy will be 0. The particle in mean position, therefore x is equal to 0. The potential energy is 0 and kinetic energy is equal to total energy E. Suppose the particle at x is equal to half of amplitude, means the position of particle is half of amplitude, x is equal to a by 2. Therefore, k is equal to half m omega square bracket a square minus a square upon 4 bracket close is equal to half m omega square, solve the bracket 3a square upon 2, sorry 3a square upon 4. 3 upon 4, take the out of the bracket, 3 upon 4 bracket 1 upon 2 m omega square a square bracket close. The bracket is, the term of bracket is the total energy is equal to 3 upon 4 into total energy E. V is equal to half m omega square a square upon 4 is equal to 1 upon 4 bracket half m omega square a square is equal to 1 upon 4 into E. That means at the particle in x, sorry, the particle in a half of amplitude, the kinetic energy is 3 upon 4th part of total energy and velocity is 1 upon 4th part of total energy. Next, at x is equal to a upon square root of 2, means the particle is, the position of particle is equal a upon square root of 2. Therefore, the kinetic energy is half of E. This solution is in the in screen. The half m omega square a square minus a square upon 2 bracket close is equal to half m omega square bracket a square upon 2 bracket square. Therefore, half bracket 1 upon 2 m omega square a square bracket close is equal to half of total energy, means kinetic energy is half of total energy at the particle's position is x is equal to a upon root 2. Then V is equal to half of m omega square a square upon 2 is equal to half bracket half m omega square a square is equal to same as a half of E. That means the that means the potential energy of this position is half of total energy. At this position, kinetic energy and potential energy will be same. That is, kinetic energy is equal to potential energy, k is equal to V. Since omega is equal to 2 pi nu, we can write the total energy as E is equal to half m omega square a square is equal to half m bracket 2 pi nu bracket square a square is equal to, solve this bracket, half 1 upon 2 into 4 is 2 pi m v square into a square. The energy of the simple harmonic oscillator is proportional to the square of amplitude of oscillations. Summary. These sessions we have discussed the phase of simple harmonic oscillators. Next, periodic time and frequency of simple harmonic motion. Then velocity and acceleration in particle in simple harmonic motion, and last total energy in simple harmonic motion. And last topic discuss the kinetic energy, potential energy and total energy and different positions of the particles. Student assignments: obtain the expression of period and frequency of linear simple harmonic motion, and next show that the energy of oscillator is proportional to the square of amplitudes. Precaps. The angular simple harmonic motion means next session we have discussed the angular simple harmonic motion, composition of two simple harmonic motions, Lissajous figures, and they are related to numericals.